For this example, we're going to graph the following polynomial function here. So taking a look at this problem, when it comes to graphing higher ordered equations, depending on the style of equation can really depend on the process that we use in order to graph it. Now, a lot of times when it comes to graphing higher ordered equations, we definitely want to solve the equation. We want to set it equal to 0 and solve it, which finds our solutions, our x-intercepts. Finding the y-intercept is also going to be helpful when it comes to these graphs here. So we're going to just find a couple of pieces of it. For the most part with these examples, they're expecting a sketch of this. So that's what I'm going to do of this. I'm going to find some major points of it and sketch it out. So first things first, in order to find our x-intercepts, our zeros, you want to take your equation, set it equal to 0, and solve it here. So if we're going to set this equation equal to 0 to solve, again, solving higher ordered equations or solving just equations in general, if you can factor the problem, start with that. If you can't factor it, then we need to look at other processes to try and get it solved. This one can definitely factor. We do have a GCF with both of our terms. That GCF is an x squared. We can pull that x squared out to the front. To figure out what goes left in the parentheses, we're going to divide out that squared, x squared. X to the fourth over x squared gives us x squared. Drop down the minus sign, and x squared over x squared cancels, leaving us with a 9. This puts the equation in factored form for us. Once your equation is in factored form, you can use the zero factor property that tells us that we can split our factors up. Again, our factors are x squared and x squared minus 9. Separate them, set them each equal to 0, and solve each one of those equations. Now this x squared is equal to 0, so in order to solve that for x, take the square root of each side, and we get x is equal to 0. That tells us that we do have a solution, which means we have an x-intercept at 0. So we know a point here does exist. We need to solve the other equation here, and solving this equation, add the 9 to each side, giving us x squared is equal to 9. Take the square root of each side, and we get that x is equal to plus or minus 3. So we also have a point here at negative 3, and over here at positive 3. Now, a couple of tidbits about this here. We can also find the y-intercept by plugging in 0 for x into our equation. Now, if we do that, if we plug in 0 for x and simplify, we're left with 0. So this 0, 0, this point that we already got, that's an x and a y-intercept there. So then just a couple other pieces to figure out here. We do know that we have these 3 zeros here that exist. One other important thing to maybe note about this example here is let's determine the end behavior of this. What is our graph looking at either end here? Now, I do have videos over determining the end behavior, so if you need a little bit more detail on that, I recommend going back and watching that. Otherwise, you do determine end behavior by looking at your leading term here. You want to pay attention, is it positive or negative, and what the degree of it is. We have a positive function that has an even power. A positive function with an even power shoots off to the left and shoots off to the right in the positive direction. Rises to the left, rises to the right. Also, this is a fourth degree function, and fourth degree functions look like W's. A positive function looks like a regular W like this. A negative fourth degree function looks like a W going downwards here. And that does fall in line with everything that we have here. So by the end behavior, we know our graph is going to rise to the left here. And so we know it's coming from this direction. And it makes sense that it's going to come from this direction and it's going to hit our first point here. Okay. Now, the next important process here, we know that this needs to look like a positive W like here. So more than likely it's going to go through here, cut here, go back up, go down, and then go back up to make that W shape. We can definitely confirm that with all the math. We did that with our points here, 0, positive 3, negative 3. We looked at our end behavior here. Other thing to look at here is the multiplicity of your zeros. This 0 over here, the x equals 0 here that we got in the middle here, has a multiplicity of a 2. Right? Multiplicity of a 2 because the power on this x was a 2. And typically, if we take a square root of 0, now 0 is not positive or negative, otherwise it would have been like a plus 0 or negative 0, but that doesn't make sense with 0. But that x had a power of 2, which means that this 0 here has a multiplicity of 2 attached to it. Over here, with the positive 3 and the negative 3, we had one positive 3 pop up, one negative 3 pop up. Those each have a multiplicity of a 1. This makes a difference on our graph. Even multiplicities will touch the 0 and turn around. Odd multiplicities are going to cross through the point. So since we know our graph is coming from this direction and it's going to hit this first point, this negative 3 has a multiplicity of 1, so it is going to cross through that point. But we know it's going to need to turn around and go back up and hit our next x-intercept here, and it needs to follow this W shape. So it's going to turn around and it's going to go back and it wants to touch this middle point here, right? It needs to touch all of our x-intercepts. Now this is our 0, 1. This 0 has a multiplicity of 2. And even multiplicities mean that they're going to touch that point and they're going to turn away. They're going to repel away from it, kind of like a magnet, right? Even multiplicities touch and go away. Odd multiplicities cut through. So this is going to turn away and go back down here. But once again, we know that it needs to turn around so that it can go back up and hit our next point here, the positive 3, that has a multiplicity of 1. And since it has a multiplicity of 1, that tells us that it's going to cut through that point and it's going to continue to shoot up and it's going to continue to rise on that side over there, just like when we found the end behavior rising on either side. This is what a sketch of this function would look like.